Hello everyone. In this lesson, we will continue to study the frequency domain analysis module of continuous system. Today, we will study sampling theorem and its application. The main contents include time domain sampling theorem, Nyquist sampling rate and a sampling interval, signal recovery, application of sampling theorem, and the frequency domain sampling theorem. First, let's take a look at time domain sampling theorem. For a signal ft with limited frequency band, if its spectrum only occupies the range from -ωm to ωm, the signal ft can be represented only by equally spaced sampling value fnts. The sampling interval must be less than 1/2 fm, which means that its time sampling interval Ts is less than 1/2 fm, or the lowest sampling frequency is 2 fm. That is to say, its sampling frequency is greater than or equal to 2 fm. This is the basic content of the time domain sampling theorem. Let's review the spectrum of time domain sampled signal. You have learned in the last lesson, if the continuous signal ft is ideally sampled, we can get its sampled signal fst. The spectrum fsj omega of the sampled signal is periodically extended according to the frequency spectrum of the original signal fj omega. In other words, the spectrum of the sampled signal is a periodic extension of the original signal spectrum. Its period is omega s. Obviously, when doing period extension, if the value of omega s is less than 2 omega m, spectrum aliasing may occur. Let's discuss the necessary conditions to recover the original signal. That is to say, what conditions are required to recover the original signal from the sample signal. According to the spectrum analysis, we know that if the spectrum is not to be aliased, Fs must be greater than or equal to 2 fm. That is to say, the frequency of the sample signal is more than twice the frequency of its original signal. If the condition is not met, spectrum aliasing will occur. Here, Ts is equal to 1/2 fm. In other words, its sampling interval cannot exceed 1/2 fm. 1/2 fm is the maximum sampling interval, which is commonly known as the Nyquist sampling time. Similarly, Fs is equal to 2 fm. It is the minimum sampling frequency, which is called the Nyquist sampling frequency. When the signal is recovered, theoretically, there is a mathematical model of its frequency domain. We have learned that the spectrum of the sample signal is the spectrum shifting of the original signal spectrum. In this way, the original signal can be recovered by a low-pass filter. So its mathematical model is very simple. The ideal low-pass filter can be denoted by formula 3. This filter's amplitude frequency characteristic is Ts. When its frequency is less than or equal to omega m, and when the absolute value of omega is greater than omega m, its amplitude frequency characteristic is 0. Its phase characteristic is not considered here. However, in practical engineering, for this filter, omega c is generally greater than omega m and less than omega s minus omega m. In this way, a certain margin can be left for the filter. Let's take a look at the mathematical model of time domain of signal recovery. In frequency domain, the signal recovery is equal to Fs times h. According to what we have learned before, the convolution in time domain corresponds to the multiplication in frequency domain. Therefore, the mathematical model of the time domain of this signal recovery is Formula 5. Ft is equal to the convolution of sample signal Fst and Ht, where Ht is the inverse Fourier transform of Hj omega. The working process of signal recovery can be represented by Figure 2. This is a sample signal. It enters an ideal low-pass filter. This process corresponds to convolution operation in time domain. The output of the ideal low-pass filter is Ft. In frequency domain, to recover the original signal is to multiply Hj omega by Fsj omega, and the output is Fj omega. As shown in the figure, this is the time domain sampled signal. This is the spectrum of the sampled signal. Such a spectrum enters a low-pass filter and its high-frequency components are filtered out. Only the low-frequency components are remained. Finally, the spectrum of Fj omega is obtained. For such an ideal low-pass filter, its frequency domain characteristic is a gate function. Well, what is its time domain characteristic? We can express its frequency characteristic by Formula 8. It is a gate function. Its width is 2 omega c. Its amplitude frequency characteristic is Ts. Obviously, its frequency domain characteristic is a gate function. We know that a gate in the frequency domain corresponds to the sample signal in the time domain. Here, if the cutoff frequency of the low-pass filter is omega s over 2, at this time, its time domain sampling interval Ts should be pi over omega c. After taking the inverse Fourier transform of Hj omega, we can get Formula 9. In other words, the time domain characteristic of this ideal low-pass filter changes according to Formula 9. Obviously, it conforms the law of sampling function. For the recovered Ft in time domain, Ft is equal to the convolution of Fst and Ht. Ht is changed according to the law of Sa, and the original sample signal is convolved with Ht. We can get such an operation. This is the expression of Fs. This is the expression of Ht. Convolve the two. According to the nature of impulse function, we can get Formula 10. This is the mathematical model of Ft. When the sampling interval Ts is equal to 1 over 2 Fm, then omega s is equal to 2 omega m. That is to say, we take the minimum sampling interval. Then Formula 10 can be expressed by Formula 11. From Formula 11, we can find that the restored Ft is formed by superimposing infinitely many sampling functions Sa. When n is equal to 0, Sa appears at the position of 0. When n is equal to 1, 2, 3 to n, Sa appears at corresponding position of Ts, 2Ts, 3Ts to nTs. The maximum value of Sa appears at nTs. Its maximum value is the value of the sample signal at nTs. In this way, Formula 11 expresses a relationship between Ft and the sampled value Fnts. Let's take a look at the waveform of the recovered signal. The recovered signal Ft is actually synthesized according to Formula 11. In this figure, we can find that the values of the recovered Ft and the original signal Ft are the same at the sampling point. and the middle points are composed of infinite SA. Of course, the sampling and recovery of signals can be simulated by software. This is the waveform of another recovered signal in frequency domain and its time domain. This is the spectrum of the sample signal. This is the spectrum of the original signal obtained by the processing of low-pass filter. And this is the synthesis of the time domain. This is a waveform simulated by software. In this simulated waveform, this black curve is a continuous function. It is a sine wave. Then it is sampled with a rectangular pulse. That is to say, the two signals are multiplied, and then the sample signal is obtained. We can find that the envelope of the sample signal changes according to the original signal. This green curve is the waveform obtained after sampling recovery. Obviously, the waveform of black curve and the green curve are completely similar. Here we can find that Ft is a signal with a relatively low frequency. The frequency of the sample signal conforms to condition that Fs is greater than 2 FM. In this case, there is no aliasing. The original signal can be fully recovered by the processing of a low-pass filter. In engineering, we can also use aliasing to broaden a signal. For example, this is a sawtooth wave, and its frequency is relatively large. If its period is t, if its sawtooth wave is sampled, the sampling interval, Ts, is equal to 5/4t. Obviously, it is larger than the original signal period. Therefore, its sampling frequency is relatively low. When we use such a sampling interval to recover a signal, we can find that the recovered signal yt is equal to ft/5. In other words, the time domain is widened, and the spectrum of yt is equal to fj5 omega. Its frequency domain is compressed. Such a phenomenon is used in actual engineering. Sampling oscilloscope uses this principle to widen high-frequency signals that are not easy to display into low-frequency signals that are easy to display. We have all used oscilloscope. When we use an oscilloscope, the signal in the oscilloscope is relatively dense, and it is not convenient for observing. Therefore, we will adjust the knob of oscilloscope to make the frequency wider. In fact, this is the working principle of oscilloscope. This figure shows the waveform of the sampled and recovered signal with aliasing. This is Ft, and this is a rectangular pulse. Obviously, its sampling frequency is relatively low, or its sampling interval is relatively large. This is the sampled signal. For this sampled signal, when it is recovered by low-pass filter, we can get such a green curve. As you can see here, there is a change between their green curve and the original Ft. It is widened, and there are certain small high-frequency glitches on the curve. In fact, this is a kind of sampling with aliasing. In engineering, the sampling theorem can also be used to digitize audio signals. We know that the audio signal is generally from 0 to 3.4 kHz, which is a low frequency. Then, when sampling the audio signal, its minimum frequency should be 6800 Hz. If Fs is equal to 8000 Hz, at this time, the sampling interval is 125 microseconds. Finally, let's talk about the frequency domain sampling theorem. According to the symmetry of time domain and frequency domain sampling theorem can be derived for a time-limited signal that is zero outside the time domain interval from -Tm to Tm. That is to say, for a time-limited signal ft, if its spectrum is fj omega, its uniform frequency interval is omega s. That is to say, we adopt a uniform sampling method. In this way, fj omega can be determined by the sampling value of fjn omega s of its sampled signal. It should be noted that ft should also be a time-limited signal. Formula 11 represents its impulse sequence in frequency domain sampling. After sampling in the frequency domain, we can get fsj omega by multiplying its original frequency spectrum fj omega with the sampling pulse delta omega t. Then we can get formula 12. According to the same method, fj omega can be further expressed by formula 12. Here, fj omega and its sampling value fjn omega s also form a certain relationship. Therefore, the corresponding spectrum of the time-limited signal can be expressed by sampling value of equally spaced frequency domain. The detailed content of frequency domain sampling theorem will be explained in digital signal processing. Let's summarize the knowledge of this lecture. Today, we have learned the time domain sampling theorem. There is a necessary condition for the time domain sampling theorem. That is to say, when we do time domain sampling, its time interval Ts should be less than or equal to 1/2 FM. Its sampling frequency is greater than or equal to 2 FM. This is a necessary condition for time domain sampling. Therefore, the Nyquist sampling rate and Nyquist sampling interval are obtained. Its minimum sampling frequency is 2 FM, and the maximum sampling interval is 1/2 FM. When a signal is recovered, the principle is very simple. According to the formula fj omega equals fsj omega times hj omega. In other words, the original signal can be recovered after the sample signal is processed by an ideal low-pass filter. Of course, its prerequisite is that the sampling theorem must be satisfied. As for the application of the sampling theorem, we learned the working principle of the sampling oscilloscope. Finally, we studied the frequency domain sampling theorem. The corresponding frequency spectrum of a time-limited signal can be represented by equally spaced frequency domain sampled value. Here, Fs is required to be less than or equal to 1/2 Tm. So much for today. Thanks for your attention. Goodbye.